Hello and welcome to the MoDyPy Basics tutorial. My name is Ralf, and in this tutorial I will show you how to linearize our water tank example around a steady state. If you are the kind of person who rather reads tutorials instead of watching them, hop over to docs.modypy.org, where you will find this tutorial series in text form. In this tutorial, we will linearize our water tank example around a steady state. And why would you want to do that? Well, one motivation is control design. There are simple methods for linear and time invariant systems, so-called LTI systems. These systems have this simple form. So the derivative of the state over time and the output are both linear combinations of the state and the input. And that makes design of controllers very simple because you can use methods from linear algebra. For nonlinear systems, the control design is more complicated. So many times when you have nonlinear systems, you try to find a linear approximation around some steady state of your nonlinear system. And to do that, we can use the linearization package in MoDyPy. For our water tank example, we see that the derivative of the height with respect to time is nonlinear in the height, and so is the outflow velocity, which just happens to be this term with the square root here. So because this is nonlinear, in order to design a linear controller, we first need to linearize it. And for that, we first determine a steady state at the working point that we would like to stabilize. And based on that steady state, we then do a local linear approximation. And for the state, this works as follows. If we look at the derivative of our height with respect to time as a function of time, the height, and the inflow velocity, then we can write it this way. We have our steady state height and we have our steady state inflow, and we can express the current height as the steady state height plus some delta, and the inflow as the steady state inflow plus some delta. And now using a Taylor approximation, we get this. So we have the value of the derivative at the steady state point plus some factor times the delta in height plus some factor in the delta in inflow velocity. And the Taylor series does not stop there. There are more terms that are of the order of the square of the height or the order of the square of the velocity or products thereof, but we will neglect them here. We want a linear approximation. And one thing that we can see is because we are at a steady state here, this part of the function is 0 and can be dropped. So in the end, we have some expression that is linear in the delta of height and the delta of inflow velocity, just as we need it for linear and time invariant system. And the factors we get by partial derivation of the function with respect to height and inflow velocity. And that can get tedious for very large and very complex systems. It is easy for our case where we have just a very simple system with just one scalar state and just one scalar input. But for more complicated systems, we want to use numerical algorithms to approximate these factors and do the work for us. And that is what you can do with the linearization package in MoDyPy. So let's look into the code. Here I have the code from our previous example where we modeled the water tank and determined a steady state. And we will reuse that because we want to linearize our system in the steady state. And to do that, we need some declarations from the MoDyPy linearization package. We need the linearization configuration and the system Jacobian function. The Jacobian name comes from the fact that the Jacobian of a multidimensional, multidependent function is simply a matrix representing all the partial derivatives of all outputs regarding all inputs. So now we set up our linearization configuration object. And the constructor requires us to specify the system that we want to linearize and the state and the input at which we want to linearize. And we get the state and the input from the result of our steady state determination. And so we can simply specify them here. And the next step would be to call the system Jacobian function, which returns 4 matrices, exactly those matrices which we require for defining our linear system, and we pass it the linconfig configuration. And then we can print our resulting matrices. Now, if we run this, we get matrices for A and B, but empty matrices for C and D. And here, this is obviously the linear influence of the height on the derivative of the height. So the height tends to diminish. And this is the influence of the inflow on the derivative of the height. Note that in both cases, it's actually the difference of height and inflow regarding the steady state. But why do we get empty output matrices? So these determine the change in the output, whatever output we specify. Well, the point is we didn't specify any output. And to do that, we would have to use the output descriptor class, and we will declare some output for us. We will declare the outflow velocity as an output signal. So first determine a signal that determines the outflow velocity. And make it a signal. And then we can here introduce the output by creating an output descriptor. We need to pass it the linearization configuration that it is part of, and we need to specify the port or signal that we want to linearize. And in that case, that is the outflow velocity. And so if we run this again, we now get entries in the output matrices here. And it seems that the higher the fill state of our tank is, the higher the outflow rate will be, but the inflow rate doesn't have any impact. And maybe that is what you actually want to do. You want to decouple the outflow from the inflow, at least to some point. So that is how you do linearization with MoDyPy. And that's also it for our MoDyPy Basics tutorial series. I hope that you learned all the major things that you need for whatever your projects are with MoDyPy, and I would like to hear from you about what you are doing with MoDyPy. Thanks for listening. Bye bye.